Imagine standing outside at night, searching the sky for the moon. But this time it isn't hiding behind clouds, it isn't in shadow, it simply isn't there anymore. No glow, no reflection on the oceans, no silver light guiding the tides, just a black empty space where Earth's oldest companion once ruled the night. In that single moment, the balance of our planet begins to unravel. The oceans start to behave strangely. Seasons slowly drift out of control. Earth's rotation, climate, and even the future of life itself begin moving toward an unknown path. What looks like a peaceful disappearance becomes the beginning of the most dangerous planetary experiment in human history. Tonight, we're going to travel far beyond the obvious consequences. We'll explore what happens in the first hours, the first centuries, and the deep future where Earth is forced to survive without the moon's stabilizing gravity. This isn't science fiction, it's real physics, real astronomy, and real consequences scientists have already modeled. If you love cosmic mysteries, deep space science, and documentaries that reveal how fragile our universe truly is, make sure to subscribe now and turn on notifications, because what you're about to see will completely change how you look at the night sky. Now, let's remove the moon from existence and watch what really happens to Earth.
For over 4 billion years, the moon has been Earth's silent companion. It rises and sets with quiet reliability, shaping our nights, stabilizing our planet, and pulling at the oceans with invisible gravitational hands. Because it has always been there, we rarely think about how deeply our world depends on it. But imagine this impossible moment. The moon vanishes instantly. No fragments, no debris, no explosion, just empty space where it once hung. The consequences would begin immediately, and they would unfold in ways both subtle and catastrophic. The first changes would not be seen in the sky, but felt in the oceans. The moon is the primary driver of Earth's tides. Its gravity pulls ocean water toward it, creating the familiar rise and fall of sea levels along coastlines. Without the moon, this gravitational tug would be drastically reduced. The sun also produces tides, but its effect is much weaker because of its immense distance. Overnight, global tides would drop to roughly 1/3 of their current strength. Coastal ecosystems that depend on tidal cycles would be thrown into chaos. Tidal pools that nurture marine life would no longer refill properly. Nutrient mixing along shorelines would slow down. Many species that rely on predictable tides to feed and reproduce would struggle to survive. Ports and harbours designed around current tidal ranges would become inefficient. Shipping routes that depend on tidal flow would be disrupted. In some regions, stagnant coastal waters could begin to accumulate pollution and debris because the natural flushing effect of tides would weaken. Over time, this would affect fisheries, coral reefs, and coastal economies that support hundreds of millions of people. But the oceans are only the beginning. The moon also acts as a stabilizer for Earth's rotation. Right now, Earth spins with a relatively stable tilt of about 23.5 degrees. This tilt is what gives us seasons. It is the reason summers are warm and winters are cold. The moon's gravitational presence prevents this tilt from wobbling wildly. Without it, Earth's axis would become unstable over long periods of time. At first, the change would not be dramatic. Days would continue to pass and seasons would still occur. But over thousands and millions of years, Earth's tilt could begin to shift unpredictably. It might swing toward extreme angles, causing brutal climate changes. Imagine a world where one hemisphere experiences continuous sunlight for months, while the other freezes in darkness. Ice caps could melt rapidly in one era and reform aggressively in another. Weather patterns would become more extreme. entire ecosystems would be forced to adapt or collapse. The length of Earth's day would also be affected. The Moon is slowly stealing rotational energy from Earth through tidal friction. This process has been gradually slowing Earth's rotation for billions of years. Without the Moon, this braking effect would largely disappear. Earth would continue spinning at nearly the same speed it has now, instead of gradually lengthening days over geological time. While humans would not notice an immediate difference, the long-term evolution of Earth's rotation would be permanently altered. Night itself would become darker than anything modern humans have experienced. The Moon reflects sunlight and provides natural illumination across the planet. Without it, nighttime landscapes would be dominated only by starlight. Rural areas would plunge into near-total darkness. No moonlit nights, no soft glow on oceans or mountains. This would affect animal behavior profoundly. Many species rely on moonlight to hunt, migrate, or avoid predators. Sea turtles, for example, use the brightness of the horizon over the ocean to guide newborn hatchlings toward the water. Without the Moon, these cues would vanish, leading to mass disorientation and population decline. Human culture would also feel the impact. The Moon has shaped calendars, mythology, religion, navigation, and art for thousands of years. Ancient civilizations measured time by lunar cycles. Farmers planned planting and harvesting by moon phases. Sailors navigated oceans using the Moon's position. Remove it, and humanity loses one of its oldest natural reference points in the sky. But beyond cultural loss, there would be practical consequences in space. The Moon acts as a gravitational shield to some extent, capturing or deflecting asteroids and comets that might otherwise strike Earth. Without it, Earth would become more exposed to cosmic debris. The increase in impact risk would not be immediate or dramatic, but over millions of years, the probability of large asteroid collisions would rise. That means more frequent mass extinction level events in Earth's future. The disappearance of the Moon would also destabilize Earth's orbital dynamics in subtle ways. While Earth would remain safely bound to the Sun, the intricate gravitational dance between Earth, Moon and Sun would be altered. Small changes in Earth's orbit could accumulate over time, affecting climate cycles such as ice ages and long-term temperature trends. Perhaps the most unsettling part is how silent and invisible the beginning of this disaster would be. There would be no explosion to warn humanity, no shockwave, no dramatic flash, just an empty sky and gradually unfolding consequences that grow worse over time. The planet would not end overnight. Civilization would not collapse instantly. Instead, Earth would slowly drift into a less stable, more chaotic future. Within the first few weeks, scientists would scramble to understand what had happened. Telescopes would search for evidence. Governments would hold emergency meetings. Panic would spread as people realized the Moon was not coming back. Conspiracy theories would explode across the internet. Some would claim alien intervention. Others would blame secret experiments. In reality, the event would represent one of the greatest unsolved mysteries in human history. Over decades, coastal cities would adapt to new tidal patterns. Infrastructure would be redesigned. Marine ecosystems would shift. Some species would vanish. Others would evolve to survive in the new conditions. Humans would adapt technologically, but the planet itself would be fundamentally changed. Over centuries, climate instability would become more noticeable. Extreme seasonal variations would stress agriculture. Food production would need to be redesigned around unpredictable weather patterns. Entire regions could become uninhabitable. Migration pressures would increase. Political tensions would rise as nations compete for stable land and resources. And over millions of years, Earth could become a very different world. A planet with violent climate swings, extreme temperature contrasts, unstable axial tilt. A harsher environment for complex life. The disappearance of the Moon would not destroy Earth instantly, but it would quietly push the planet onto a more dangerous evolutionary path. What makes this scenario so powerful is that the moon feels permanent. It feels eternal. Yet, in cosmic terms, it is temporary. The moon is slowly drifting away from Earth even now, moving about 4 centimeters farther each year. Billions of years from now, it will appear smaller in the sky. Solar eclipses will no longer happen, and eventually, Earth and the moon will become tidally locked, showing the same face to each other forever. The moon's disappearance, whether sudden or gradual, reminds us how fragile planetary systems truly are. Earth's stability is not guaranteed by fate. It is the result of precise cosmic conditions that just happened to align. Change one piece of the system, and everything else begins to shift. As we move deeper into this exploration, we will examine how Earth's gravity would respond, how the atmosphere might change, how life would struggle to adapt, and what the long-term fate of humanity could look like in a moonless world. Because when the moon disappears, it does not simply leave an empty sky. It leaves behind a chain reaction that reshapes the future of an entire planet. When the moon disappears, the most dramatic effects do not arrive all at once. Instead, Earth enters a slow transformation phase, a period where invisible forces quietly reshape the planet's systems. Gravity, atmosphere, oceans, and even Earth's internal rhythms begin to drift away from the balance they have maintained for billions of years. One of the first subtle but powerful changes would involve Earth's gravitational environment. The moon does more than pull on oceans. It also interacts with Earth's mantle and crust. Lunar gravity creates tiny but constant deformations in Earth's solid body called Earth tides. These microscopic flexes help dissipate internal energy and subtly influence tectonic activity. Without the moon, Earth would become slightly more rigid. Over long periods, this could change stress distribution along fault lines. While it would not immediately cause earthquakes, it could alter the long-term behavior of tectonic plates and volcanic systems. The oceans, already weakened by reduced tides, would begin to show deeper consequences. Tides play a critical role in mixing ocean layers. They help circulate nutrients from deep water to the surface and move oxygen downward into darker depths. Without strong tidal mixing, ocean stratification would increase. Warm surface water would sit above colder deep water with less interaction between layers. This would slowly starve surface ecosystems of nutrients and reduce oxygen availability in deeper regions. Dead zones, areas with dangerously low oxygen, would expand. Fish populations would decline. Coral reefs would struggle to survive. Entire marine food chains could collapse. Since oceans produce more than half of Earth's oxygen through microscopic phytoplankton, this disruption could eventually affect atmospheric oxygen levels. Not immediately, but over centuries and millennia, the balance between oxygen production and consumption could shift. Weather patterns would also begin to change. The moon influences atmospheric tides, subtle pressure waves in Earth's atmosphere driven by lunar gravity. These effects are small compared to solar heating, but they contribute to long-term atmospheric stability. Without lunar influence, atmospheric circulation would become slightly more chaotic. Jet streams could become less predictable. Seasonal weather cycles might grow more extreme. Storm systems could intensify in some regions while weakening in others. Earth's rotation would continue at nearly the same speed, but the lack of lunar braking would change long-term rotational evolution. Over millions of years, Earth's day length would stop increasing as it has been doing since ancient times. This may sound insignificant, but rotational speed affects atmospheric circulation, wind patterns, and ocean currents. Faster rotation strengthens the Coriolis effect, which influences how storms spin and how global wind belts form. Even small long-term differences could amplify climate instability. Another major consequence would be the loss of eclipses. Solar eclipses happen because the moon appears almost exactly the same size as the sun in Earth's sky. This coincidence has played an unexpected role in scientific discovery. Early astronomers used eclipses to study the sun's corona and test Einstein's theory of relativity. Without the moon, this natural cosmic laboratory would disappear. Humanity would lose one of its most valuable tools for studying fundamental physics. Night skies would change permanently. Without moonlight, the Milky Way would appear brighter and clearer from most locations. While this might seem beautiful, the psychological and biological effects could be profound. Humans evolved with a lunar cycle that influenced sleep patterns, hormone production, and circadian rhythms. Many studies suggest that full moons subtly affect human sleep quality even today. Without the moon, biological rhythms could shift. Insomnia rates might increase. Wildlife behavior would be permanently altered. Animals that depend on lunar cycles would suffer the most. Predators that hunt under moonlight would lose visibility. Prey species that rely on darkness for protection would face new vulnerabilities. Migration patterns guided by lunar position would break down. Insects that synchronize reproduction with moon phases could fail to reproduce efficiently. These disruptions would ripple through ecosystems, causing cascading effects across entire food webs. Human technology would compensate in many ways. Artificial lighting would replace moonlight in cities. Navigation systems would rely more heavily on satellites. Climate engineering efforts might be attempted to stabilize agriculture. But technological solutions cannot fully replace planetary-scale gravitational systems. One of the most concerning long-term consequences involves Earth's axial tilt instability. Without lunar stabilization, Earth's tilt could vary chaotically between extremes. In one scenario, Earth's axis could tilt dramatically, approaching angles above 45 degrees. This would cause extreme seasonal shifts. Polar regions could receive direct sunlight for long periods, melting ice caps completely. Meanwhile, equatorial regions could experience massive temperature swings. Ice ages could begin and end rapidly. Sea levels would rise and fall violently. Coastal cities would flood, then re-emerge, then flood again. Such instability would make long-term civilization planning extremely difficult. Infrastructure designed for stable climates would fail. Agriculture zones would shift constantly. Water availability would become unpredictable. Entire nations might need to relocate multiple times across centuries. Earth's magnetic field could also be affected indirectly. While the moon does not generate Earth's magnetic field, changes in Earth's rotation and internal energy dissipation could influence the geodynamo process in the planet's core. Over millions of years, this could alter the strength and stability of the magnetic field. A weaker magnetic field would allow more cosmic radiation to reach Earth's surface, increasing cancer risks and damaging ecosystems. The psychological impact on humanity should not be underestimated. The moon has always been part of human identity. It appears in poetry, religion, folklore, and national symbols. Losing it would create a sense of cosmic vulnerability. People would realize that even the most familiar features of the universe are temporary. This could spark existential anxiety, philosophical shifts, and new belief systems centered on humanity's fragility. Space exploration would also change. Without the moon as a nearby stepping stone, missions to Mars and beyond would become more challenging. The moon currently serves as a potential base for fuel production, scientific research, and deep space launch platforms. Its disappearance would force humanity to redesign long-term space expansion strategies. Ironically, the moon's absence might accelerate technological innovation. Scientists would rush to understand gravitational stability. Engineers would develop new climate control systems. Space agencies would prioritize planetary defense and orbital engineering. Humanity might even attempt artificial moons, massive orbital structures designed to restore some gravitational stability. While this sounds like science fiction, future civilizations may seriously consider building large-scale orbital habitats or gravity generators. But no artificial structure could fully replace the moon's natural influence. Its mass, distance, and gravitational interaction are perfectly tuned by cosmic chance. Reproducing that balance artificially would require technology far beyond anything humanity currently possesses. As centuries pass, Earth would become increasingly unpredictable. Some regions might remain habitable and stable, others would become hostile. Civilization would survive, but it would look very different. Cities might cluster in narrow, climate-safe zones. Food production could rely heavily on controlled environments like vertical farms and artificial ecosystems. And still, the long-term trajectory would remain uncertain. Without the moon, Earth would no longer be a stable platform for life as we know it. It would become a planet constantly adjusting to shifting gravitational and climatic conditions. This slow transformation is what makes the moon's disappearance so unsettling. There is no single dramatic apocalypse, no instant destruction. Instead, Earth quietly drifts away from stability, day by day, century by century, into a future that becomes harder to predict with every passing generation. In the next stage of this scenario, we will explore how Earth's orbit itself could evolve, how long-term climate cycles might spiral into extremes, and what this means for the ultimate survival of complex life on a moonless world. Because when the moon vanishes, the story does not end. It only begins. As the centuries pass without the moon, Earth's transformation becomes more pronounced. What began as subtle gravitational and ecological changes slowly evolves into planetary-scale consequences. The most critical shift now unfolds in Earth's long-term orbital behavior and climate stability. While Earth remains bound to the Sun, the Moon's absence removes a stabilizing partner that once helped regulate Earth's motion through space. Normally, Earth and the Moon orbit a shared center of mass. This relationship creates small but important gravitational feedback loops that smooth out variations in Earth's orbit. Without the Moon, Earth becomes more vulnerable to the gravitational influence of other planets, especially Jupiter and Venus. Over thousands and millions of years, these interactions can slightly alter Earth's orbital eccentricity, how elliptical its orbit becomes, and affect how much sunlight Earth receives at different times of the year. Even small orbital changes can trigger dramatic climate consequences. Ice ages on Earth have historically been influenced by orbital cycles known as Milankovitch cycles. These cycles affect how solar energy is distributed across the planet. Without the Moon's stabilizing presence, these cycles could become more chaotic and extreme. Instead of slow, predictable climate rhythms, Earth could experience abrupt transitions between warm and cold periods. Glaciers might expand rapidly and then retreat just as fast. Sea levels would rise and fall repeatedly, reshaping coastlines and flooding low-lying regions. As climate instability increases, ecosystems face enormous pressure. Forests that evolved for stable seasonal patterns may no longer survive. Tropical regions could swing between extreme droughts and intense rainfall. Polar regions could experience periods of intense warming followed by deep freezes. Species migration patterns would accelerate as animals and plants attempt to follow shifting climate zones. Many would fail to adapt quickly enough, leading to widespread extinctions. Human civilization would be forced to respond. Agriculture would become one of the most vulnerable systems. Crops rely on predictable seasons and rainfall cycles. With increasing climate unpredictability, traditional farming methods would struggle. Governments and scientists would invest heavily in controlled environment agriculture, massive indoor farms, climate-controlled greenhouses, and genetically engineered crops designed to survive extreme conditions. Food production would become more technologically dependent than ever before. Coastal megacities would face repeated threats from unstable sea levels. Rising oceans would flood infrastructure, while sudden drops in sea level could strand ports and shipping lanes. Massive relocation efforts would become necessary. Entire populations might migrate inland or toward more stable climate zones. Political tensions would rise as nations compete for habitable land and freshwater resources. Freshwater availability itself would become a major concern. Changes in precipitation patterns would alter river systems and underground aquifers. Some regions might experience severe water shortages, while others face constant flooding. Large-scale water management projects, including desalination plants, artificial reservoirs, and atmospheric water capture, would become essential to sustaining civilization. Meanwhile, Earth's vulnerability to space hazards would continue to grow. Without the Moon acting as a partial gravitational shield, Earth would face an increased risk of asteroid and comet impacts. The Moon currently absorbs a portion of incoming debris, evident from its heavily cratered surface. Without it, more objects would pass closer to Earth's orbit. Over long periods, the probability of catastrophic impacts would rise. Humanity would likely respond by expanding planetary defense systems. Space agencies would develop advanced asteroid detection networks, deflection technologies, and interception systems. Massive space telescopes would scan the skies constantly, searching for potential threats. Laser systems, kinetic impactors, and gravitational tug devices could become standard tools for protecting Earth. While this technology could reduce risk, it would never eliminate it completely. The psychological and cultural transformation of humanity would deepen. Without the Moon, the night sky would feel unfamiliar. Ancient stories tied to lunar cycles would fade into history. New myths would emerge, centered around Earth's fragility and humanity's responsibility to protect its planet. Philosophical movements might arise that emphasize planetary stewardship and long-term survival rather than short-term progress. Religion and spirituality could also shift. Some groups might interpret the Moon's disappearance as a cosmic warning or a test of humanity's resilience. Others might see it as proof that the universe is indifferent to human existence. These differing interpretations could influence politics, education, and global cooperation. Scientific research would accelerate dramatically. Understanding Earth's new dynamics would become one of humanity's top priorities. Climate modelling, orbital mechanics, and planetary physics would receive unprecedented funding. New international research alliances would form to share data and coordinate planetary stabilization efforts. One ambitious idea might involve artificial gravitational stabilization. Future engineers could attempt to place massive orbital structures around Earth to simulate some of the Moon's stabilizing effects. These could include large space habitats, asteroid-based gravity anchors, or even artificially constructed micromoons. While such projects would be extremely expensive and technologically challenging, desperate times often drive extraordinary innovation. Another potential adaptation could involve altering Earth's atmosphere to regulate climate. Geoengineering projects might attempt to control solar radiation by injecting reflective particles into the upper atmosphere, or deploying space-based sunshades. While these methods could stabilize temperature temporarily, they would carry risks and unintended consequences that could further complicate Earth's environment. Human settlements might also expand beyond Earth. As conditions become less stable, off-world colonies on Mars, orbital stations, and artificial habitats could become more attractive. Humanity might diversify its presence across multiple locations in the solar system as a survival strategy. The Moon's disappearance could, ironically, accelerate humanity's transition into a multi-planetary species. But even with advanced technology, Earth's natural systems would remain under stress. Biodiversity loss would continue as ecosystems struggle to adapt. Pollinator populations could decline, affecting food production. Ocean acidification and temperature changes could disrupt marine life further. Coral reefs might vanish entirely in some regions, removing critical marine habitats. Over thousands of years, Earth could begin to resemble a planet in constant environmental flux. Habitable zones would shift. Some regions would become permanently uninhabitable. while others might emerge as new centers of life and civilization. Human culture would adapt to a world where change is constant and stability is rare. What makes this transformation especially unsettling is its slow pace. No single generation would witness the full consequences. Instead, each generation would inherit a slightly more unstable planet than the one before. The changes would feel gradual, almost invisible at first. But over long time scales, they would accumulate into dramatic planetary evolution. The disappearance of the Moon would mark the end of Earth's long era of relative stability. For billions of years, Earth has maintained conditions suitable for complex life. That balance was never guaranteed. It existed because of a rare combination of cosmic circumstances: the right distance from the Sun, the presence of a large stabilizing moon, a protective magnetic field, and an atmosphere capable of regulating temperature. Remove one of those pillars, and the entire system begins to shift. As humanity moves deeper into this altered future, the question becomes not just how to survive, but how to preserve what makes Earth unique. Can civilization maintain biodiversity, cultural identity, and planetary health in a world without the Moon? Or will Earth slowly drift toward a harsher, less hospitable state, where life becomes increasingly fragile? In the next phase of this scenario, we will explore the deepest long-term consequences, how Earth's internal systems evolve, how life itself may change genetically to survive new conditions, and what the ultimate fate of a moonless Earth might look like millions of years into the future. Because the disappearance of the Moon is not just a loss in the sky, it is the beginning of a new chapter in Earth's cosmic story. As millennia pass without the Moon, Earth no longer resembles the stable world humanity once knew. The planet continues to function, oceans still move, winds still blow, and life still persists, but the rhythm of nature becomes unpredictable and harsh. What was once a finely balanced system now behaves like a constantly shifting machine, adjusting itself in unstable ways. One of the most dramatic long-term changes occurs in Earth's biosphere. Species that once thrived under predictable seasonal cycles now face continuous environmental stress. Plants evolve faster-growing life cycles to adapt to unstable climates. Some species develop greater resistance to temperature extremes, while others retreat into narrow ecological niches where conditions remain relatively stable. Forests begin to change composition. Large, slow-growing trees become less common in unstable climates. Faster-growing, resilient plant species dominate. Grasslands expand in regions that experience repeated drought and flooding cycles. Tropical rainforests shrink in some areas while expanding into newly warm zones closer to the poles during extreme tilt phases. Animal populations follow similar trends. Species with flexible diets and high reproductive rates gain an advantage. Specialized species that depend on narrow environmental conditions struggle to survive. Migration patterns intensify as animals chase moving climate zones. Some species develop new behaviors, such as altered breeding seasons or nocturnal activity shifts to adapt to changing temperature cycles. Marine ecosystems face even greater pressure. With weakened tides and altered ocean circulation, nutrient distribution becomes less efficient. Plankton populations fluctuate dramatically. Since plankton form the base of the marine food chain, these fluctuations ripple upward, affecting fish stocks, marine mammals, and seabirds. In some regions, oceans become warmer and more stagnant. Coral reefs, already sensitive to temperature changes, suffer massive die-offs. Entire reef ecosystems collapse, removing critical habitats for thousands of species. Coastal communities that depend on fishing experience long-term food shortages, forcing further human migration. Over thousands of years, life on Earth begins to evolve differently. Natural selection favors organisms that tolerate instability rather than consistency. Genetic diversity becomes a survival advantage. Populations with greater genetic variation adapt faster to sudden environmental shifts. This accelerates evolutionary processes, leading to rapid emergence of new species while others vanish. Humans are not immune to these pressures. While technology offers protection, biology still responds to environmental stress. Over many generations, human populations living in extreme climates may develop physiological adaptations. These could include improved heat tolerance, altered metabolism, or changes in circadian rhythms due to darker nights and irregular seasonal cycles. Human settlements transform as well. Cities become more modular and adaptable. Instead of sprawling megacities vulnerable to climate shifts, humanity builds flexible urban systems that can be relocated or reconfigured. Floating cities emerge in regions affected by unstable sea levels. Underground habitats become more common in extreme temperature zones. Architecture evolves to withstand constant environmental stress. Buildings are designed with dynamic insulation systems, adjustable ventilation structures, and climate-responsive materials. Entire districts can be sealed during extreme weather events. Energy production shifts heavily toward renewable sources combined with advanced storage systems to stabilize power supply during environmental disruptions. Food production becomes one of humanity's most advanced technological fields. Vertical farms dominate urban centers. Crops are grown under artificial lighting with precisely controlled conditions. Genetic engineering produces plants that grow faster, require less water, and resist disease. Livestock farming declines in many regions, replaced by lab-grown protein and alternative food sources. Water management becomes equally critical. Desalination plants operate at massive scales. Atmospheric water harvesting systems extract moisture directly from air in dry regions. Artificial rivers and controlled reservoirs regulate water distribution across continents. Entire global networks coordinate freshwater supply to prevent shortages. At the same time, humanity's relationship with space deepens. With Earth becoming less stable, off-world expansion accelerates. Mars colonies grow. Orbital habitats become permanent population centers. Asteroid mining operations provide raw materials for construction and manufacturing. Humanity slowly transforms into a spacefaring civilization not by ambition alone, but by necessity. Artificial gravity habitats begin to simulate lunar-like gravitational environments to compensate for the Moon's loss. Engineers experiment with rotating space stations and massive orbital rings that generate centrifugal gravity. These structures not only support human life, but also serve as research platforms to study long-term adaptation to different gravitational conditions. Some visionary projects even attempt to recreate the Moon's stabilizing role. While building a replacement Moon is beyond practical feasibility, large-scale orbital mass systems could slightly influence Earth's gravitational environment. These projects remain experimental and controversial, but they demonstrate humanity's willingness to reshape planetary-scale systems. Cultural identity also evolves. The Moon, once central to mythology and art, becomes a symbol of loss and transformation. New generations grow up without ever seeing it. Stories of moonlit nights become legends. Artists and writers depict the Moon as a lost guardian of Earth. Memorial observatories are built to preserve humanity's memory of the lunar era. New cultural traditions emerge centered around Earth's resilience. Annual planetary awareness days celebrate humanity's survival and adaptation. Educational systems focus heavily on planetary science, environmental engineering, and long-term sustainability. Children are taught that Earth is no longer naturally stable and that protecting planetary systems is a collective responsibility. Religion and philosophy continue to adapt. Some belief systems interpret the Moon's disappearance as evidence that the universe is dynamic and unpredictable. Others see it as a reminder of humanity's duty to preserve life regardless of cosmic uncertainty. Philosophical movements arise that emphasize adaptability, long-term thinking, and planetary unity. Politically, Earth moves toward greater global cooperation. Climate instability forces nations to collaborate on resource distribution, disaster response, and infrastructure development. While conflicts still exist, the shared challenge of planetary survival encourages stronger international institutions. Global early warning systems monitor climate patterns, tectonic activity, and space threats. Artificial intelligence plays a major role in forecasting environmental shifts and coordinating large-scale responses. Humanity becomes increasingly dependent on predictive modeling to stay ahead of Earth's changing behavior. Over tens of thousands of years, Earth's appearance continues to evolve. Ice sheets grow and shrink rapidly depending on axial tilt cycles. Deserts expand into regions that once supported forests. New ecosystems emerge in unexpected places. Life adapts, but biodiversity remains under constant pressure. Despite all these challenges, Earth does not become lifeless. Instead, it becomes more extreme. Life persists in resilient forms. Humans remain, though their civilization looks radically different from the one that once gazed at a bright moon in the night sky. What makes this future so remarkable is humanity's transformation alongside the planet. Instead of remaining passive observers, humans become active planetary engineers. They learn to manage climate systems, regulate ecosystems, and stabilize human habitats. Civilization evolves from exploiting nature to carefully maintaining it. However, this new role comes with risks. Large-scale planetary engineering can produce unintended consequences. Small errors in climate manipulation could trigger new disasters. Ethical debates arise about how much control humanity should exert over natural systems. Questions about who decides planetary policies become increasingly important. The moon's disappearance forces humanity to confront a deeper truth. Planetary stability is not guaranteed. Earth was once protected by rare cosmic conditions. Without them, survival requires constant effort, cooperation, and innovation. As centuries become millennia, Earth gradually settles into a new equilibrium. Not as stable as before, but not completely chaotic either. Climate systems fluctuate within broader ranges. Ecosystems reorganize. Human civilization adapts to this new reality, yet the long-term future remains uncertain. Without lunar stabilization, Earth's axial tilt could eventually reach extreme values that push the planet into conditions similar to those of Mars or Venus-like climate states. Scientists monitor these trends carefully, searching for ways to counteract dangerous shifts. Some theories suggest that in the far future, Earth could become too unstable to support large-scale surface life. If this happens, humanity may rely more heavily on artificial habitats, underground cities, and space colonies. Earth would remain home, but not necessarily the primary center of civilization. This possibility reshapes humanity's long-term goals. Instead of viewing Earth as the permanent cradle of civilization, humans begin to see it as one chapter in a larger cosmic journey. The disappearance of the moon becomes the moment when humanity transitions from planetary dependence to multi-world survival. In the next phase of this scenario, we will explore the far future, millions of years ahead, when Earth's orbit, climate, and internal dynamics continue to evolve, and when humanity must decide whether to remain tied to a changing planet or fully embrace life beyond Earth. Because when the moon disappears, it does not simply change Earth's environment, it changes humanity's destiny. As time stretches into hundreds of thousands and then millions of years, the absence of the moon reshapes Earth on the deepest geological and planetary scales. What once felt like slow environmental change now becomes a fundamental transformation of the planet's identity. Earth is no longer the calm, predictable world that supported stable civilizations for most of human history. It becomes a dynamic, evolving system that constantly shifts between extremes. One of the most dramatic long-term consequences is the increasing instability of Earth's axial tilt. Without the moon acting as a stabilizing anchor, Earth's tilt begins to wander more freely. Over long periods, it can swing between moderate angles and extreme orientations. When the tilt grows large, entire hemispheres experience prolonged exposure to sunlight, while the opposite side falls into extended darkness. During extreme tilt phases, polar regions can become temporary tropics. Ice sheets melt rapidly, releasing enormous volumes of freshwater into the oceans. Sea levels rise dramatically, flooding low-lying continents and reshaping coastlines. At the same time, equatorial regions may experience colder, darker seasons that disrupt agriculture and ecosystems. When the tilt swings back in the opposite direction, temperatures drop sharply. Newly formed oceans freeze. Ice sheets expand across continents. Massive glaciers carve landscapes and push ecosystems towards the equator. This constant oscillation between extreme heat and cold creates a planet that is always in transition, never settling into long-term climatic balance. These changes profoundly affect Earth's atmosphere. Rapid warming phases increase evaporation and atmospheric moisture, intensifying storms and rainfall. Cooling phases reduce atmospheric water content, increasing aridity and dust circulation. Wind patterns shift dramatically as temperature gradients change between regions. Over time, these atmospheric shifts alter the chemical composition of the air. Increased volcanic activity, triggered by changing tectonic stress patterns, releases additional gases into the atmosphere. Without stable climate regulation, greenhouse gas cycles fluctuate more strongly, sometimes amplifying warming periods and deepening cooling phases. Earth's oceans also evolve in new ways. As ice melts and refreezes repeatedly, ocean salinity changes. Circulation currents weaken in some areas and intensify in others. The global conveyor belt that once regulated temperature distribution becomes less reliable. Some regions experience long-term stagnation, while others face powerful current surges. Marine ecosystems continue adapting, but biodiversity remains under constant pressure. Species that can tolerate wide temperature ranges dominate. Deep-sea organisms, protected from surface fluctuations, become increasingly important to ocean stability. Coastal ecosystems, once among the most productive on Earth, become unstable due to fluctuating sea levels and weakened tidal forces. On land, ecosystems reorganize around resilience rather than specialization. Forests become more mixed and adaptable. Grasslands expand and contract with climate cycles. Deserts grow in some regions and retreat in others. Life does not disappear, but it becomes more rugged and opportunistic. Human civilization, now far more technologically advanced, adapts alongside these changes. Large populations no longer depend solely on Earth's surface. Underground cities protect inhabitants from extreme temperatures and radiation fluctuations. Floating habitats adjust position based on sea level changes. Space-based settlements become permanent centers of population and industry. Energy production shifts toward planetary-scale systems. Solar arrays in orbit collect energy continuously and beam it to Earth. Fusion reactors provide stable power independent of environmental conditions. These technologies allow humanity to maintain stable living conditions even as the planet itself becomes unpredictable. Transportation systems evolve to handle global instability. High-speed underground transit networks connect major population centers. Autonomous cargo systems move food and resources between regions. Atmospheric flight becomes less reliable during extreme climate phases, pushing humanity towards space-based logistics networks. Food production becomes almost entirely controlled. Natural agriculture still exists in stable zones, but most food is grown in sealed environments. Artificial ecosystems simulate ideal conditions for plant growth regardless of external climate. Genetic engineering allows crops to survive under lower light levels and fluctuating temperatures. Human biology may also begin to change subtly. Over many generations, populations adapt to altered light cycles, darker nights, and irregular seasonal rhythms. Artificial lighting environments influence circadian biology. Some groups may even modify themselves genetically to better tolerate environmental stress. Cultural identity evolves dramatically. The idea of Earth as a permanent paradise fades. Instead, humanity views the planet as a dynamic world that must be actively managed. Education emphasizes long-term planetary science and survival strategy. Children grow up understanding that stability is something that must be created, not assumed. Art and philosophy reflect this new reality. Themes of transformation, adaptation, and cosmic fragility dominate creative expression. The lost moon becomes a symbol of a calmer past, remembered through archives, holographic recreations, and historical records. Moon festivals commemorate humanity's transition from natural stability to technological survival. Religion and belief systems continue evolving. Some traditions interpret the moon's disappearance as a natural step in cosmic evolution. Others see it as a warning about humanity's vulnerability. New belief systems emphasize responsibility toward planetary systems and intergenerational stewardship. Politically, Earth becomes increasingly unified. Planetary scale challenges require coordinated response. Governments merge resources to manage climate stabilization projects, space defense networks, and global infrastructure. While conflicts still occur, the survival imperative encourages stronger international cooperation. Advanced artificial intelligence systems become central to managing Earth's complex environment. These systems analyze climate data, predict orbital shifts, coordinate resource distribution, and optimize planetary engineering efforts. Humans remain decision makers, but AI assists in handling the overwhelming complexity of a constantly changing planet. Meanwhile, Earth's geological systems continue evolving. Changes in rotational dynamics slightly alter stress distribution within the mantle. Volcanic activity patterns shift. Some regions experience increased eruptions, releasing gases and reshaping landscapes. Others become more geologically quiet. Mountain ranges erode faster during extreme climate cycles. New river systems form as glaciers advance and retreat. Entire continents slowly reshape themselves. Earth becomes a planet in motion not only through space but through constant surface transformation. Over millions of years, life on Earth becomes more resilient but also more fragmented. Isolated ecosystems develop unique evolutionary paths. Some species adapt to extreme cold, others to intense heat. New life forms emerge, better suited to fluctuating environments. Evolution accelerates under constant environmental pressure. Human civilization, now spanning Earth and space, begins to view itself as a long-term cosmic species. Survival planning extends thousands and millions of years into the future. Scientists model Earth's future tilt cycles and orbital behavior, searching for ways to stabilize the planet artificially. One radical proposal involves using massive space structures to apply controlled gravitational forces to Earth. While technically challenging, such projects could slightly influence Earth's rotation and tilt over long periods. Another idea involves altering Earth's mass distribution by moving large volumes of material through planetary engineering. These projects remain controversial. Ethical debates arise about whether humanity should interfere so deeply with planetary systems. Some argue that adaptation is better than control. Others believe stabilization is necessary to preserve life on Earth. As humanity debates these choices, Earth continues its slow transformation. The planet remains alive, but different. It is no longer a naturally balanced world. It is a world shaped by constant motion, technological intervention, and evolutionary pressure. In this far future, the memory of the moon becomes more symbolic than practical. Few living humans have ever experienced moonlight, yet its legacy remains embedded in Earth's history. The moon once protected Earth's stability and allowed complex life to flourish. Its disappearance marked the beginning of a new era, an era where survival depends not on cosmic luck, but on intelligence, cooperation, and innovation. As the story continues, we must now look even further ahead. What happens when Earth's instability reaches its most extreme phases? What becomes of life when planetary conditions push beyond natural limits? And will humanity remain tied to Earth, or eventually move beyond it entirely? Because the disappearance of the Moon does not simply change the planet, it changes the long-term direction of life itself. As millions of years pass, the Moon's absence reshapes not only Earth's surface and climate, but the deeper relationship between humanity and the planet itself. Civilization no longer thinks in decades or centuries. It plans in geological timescales. Earth becomes a world that must be actively managed, monitored, and stabilized in ways no previous generation could have imagined. One of the most critical challenges in this era is maintaining planetary habitability. Without lunar stabilization, Earth's axial tilt continues to fluctuate unpredictably. Climate models project cycles of extreme heating and cooling that threaten surface ecosystems and infrastructure. To counter this, humanity begins constructing massive planetary control systems designed to regulate temperature and atmospheric balance. Space-based solar reflectors are deployed at strategic points between Earth and the Sun. These structures adjust incoming solar radiation, reducing overheating during extreme tilt phases and increasing warmth during colder cycles. Unlike simple sunshades, these reflectors operate dynamically, adjusting position and reflectivity based on real-time climate data. At the same time, atmospheric engineering becomes more advanced. Carefully controlled aerosol dispersal systems regulate cloud formation and reflect excess sunlight. Carbon capture technologies remove excess greenhouse gases during warming phases and release stored carbon during cooling periods to stabilize global temperature. These systems operate continuously, creating an artificial climate control network around the planet. Earth's oceans are also actively managed. Artificial current generators help maintain global circulation patterns that once depended on natural tidal forces. These underwater systems move water between ocean layers, restoring nutrient flow and oxygen distribution. Floating platforms regulate temperature in critical marine zones to protect biodiversity hotspots. Despite these technological efforts, nature continues to challenge human control. Unexpected feedback loops emerge. Adjustments in one region trigger unforeseen consequences in another. Scientists constantly refine models, learning that planetary systems are more complex than any simulation can fully predict. Human settlements adapt further. Surface cities shrink in importance as underground and orbital habitats grow. Subterranean megacities provide stable temperature environments protected from surface climate extremes. These cities use geothermal energy and recycled resources to sustain large populations independent of surface conditions. Orbital habitats become permanent homes for millions. Rotating space stations simulate gravity, while advanced shielding protects inhabitants from radiation. These habitats function as research centers, manufacturing hubs, and cultural centers. Some communities choose to live entirely off Earth, marking the beginning of humanity's true expansion beyond its home planet. Transportation between Earth and space becomes routine. Massive space elevators and electromagnetic launch systems reduce the energy cost of moving people and materials. Earth's orbit becomes crowded with infrastructure. Energy collectors, communication networks, climate control platforms, and defense systems. With increased reliance on artificial systems, humanity faces new vulnerabilities. Cybersecurity becomes critical as planetary control networks must be protected from malfunction and sabotage. Redundant systems are built to prevent catastrophic failures. Entire teams of specialists monitor planetary infrastructure around the clock. Human culture adapts to this new reality. The concept of natural Earth fades. Instead, people grow up understanding that Earth is a managed environment maintained through constant effort. Education focuses heavily on systems engineering, environmental science, and long-term sustainability. Children learn planetary stewardship as a core subject. They study orbital mechanics alongside biology. They understand climate feedback loops as easily as previous generations learned basic geography. This shift reflects a civilization that has become inseparable from planetary management. Art and media also evolve. Stories of the ancient moon become legendary, portrayed in immersive simulations that allow people to experience moonlit nights that no longer exist. Museums preserve records of Earth's past stability. Virtual reality recreates lunar eclipses, tides, and ancient night skies for educational and cultural purposes. Religion and philosophy continue to transform. Some belief systems emphasize humanity's role as caretaker of Earth, seeing technological stewardship as a sacred responsibility. Others emphasize humility, warning that excessive control over natural systems could lead to unforeseen consequences. Political systems adapt to planetary governance. Traditional nation-based authority becomes less dominant as global institutions manage climate stabilization, orbital infrastructure, and space security. Decision-making becomes more centralized around planetary survival goals, though local cultural autonomy remains important. Conflicts still arise, especially over access to space infrastructure and energy resources. However, the shared necessity of maintaining Earth's habitability discourages large-scale warfare. Destroying planetary systems would threaten everyone, creating a strong incentive for cooperation. Meanwhile, Earth's biological evolution continues under artificial influence. Genetic engineering becomes increasingly integrated with natural evolution. Scientists design resilient plant species capable of surviving extreme temperature swings and low-light conditions. New marine organisms are engineered to restore damaged ecosystems. Some human populations choose genetic adaptation as well. Enhanced radiation resistance, improved temperature tolerance, and altered circadian rhythms become possible through biotechnology. Ethical debates intensify over how much humanity should modify itself to survive environmental instability. As centuries pass, humanity becomes a hybrid civilization, part biological, part technological, deeply integrated with artificial systems that sustain life. The line between natural evolution and engineered adaptation blurs. Earth's role within the solar system also changes. It becomes one of several major population centers rather than the sole home of humanity. Mars settlements expand, orbital cities flourish, and asteroid colonies extract resources for construction and manufacturing. Some communities choose to permanently leave Earth, seeking stability in controlled space habitats rather than adapting to Earth's unpredictable climate cycles. Others remain deeply attached to the planet, determined to preserve it as humanity's birthplace. This divergence creates cultural differences. Earth-centered societies emphasize environmental restoration and planetary identity. Space-based societies prioritize technological independence and adaptability. Both coexist, forming a multi-location civilization connected through shared communication networks. Despite these advances, Earth continues to drift through long-term orbital and axial changes. Even with climate control systems, extreme tilt cycles place enormous strain on planetary management infrastructure. Engineers constantly upgrade systems to handle stronger temperature gradients and more volatile weather patterns. At the same time, Earth's geological activity responds to changes in rotation and stress distribution. Some regions experience increased tectonic movement. Volcanoes become more active in certain zones, releasing gases and reshaping landscapes. These geological changes add another layer of complexity to planetary management. Humanity develops advanced monitoring networks that track seismic activity, magma flow, and crustal movement in real time. Automated response systems evacuate populations and deploy protective measures during geological events. These technologies reduce disaster casualties but cannot eliminate risk entirely. As millions of years continue to pass, Earth becomes a planet where survival is possible but never effortless. Stability is no longer a natural condition. It is an engineered achievement that must be constantly maintained. Yet within this challenge lies opportunity. Humanity develops unprecedented knowledge of planetary systems. Scientists understand climate, geology, and atmospheric dynamics at levels unimaginable in earlier eras. This knowledge not only sustains Earth, but also prepares humanity to terraform other worlds. Experiments on Mars and distant moons benefit from lessons learned on Earth. Terraforming projects apply climate regulation, atmospheric engineering, and ecosystem design techniques refined during Earth's stabilization efforts. Humanity slowly transforms barren worlds into habitable environments. The disappearance of the Moon thus becomes a turning point in cosmic history. What began as a loss evolves into a catalyst for planetary mastery and interplanetary expansion. Humanity becomes capable of shaping environments on a planetary scale. However, this power comes with responsibility. Mistakes could lead to irreversible damage. Ethical questions grow more complex. Who decides how planets should be shaped? What rights do future generations have over planetary systems? These questions define the next stage of civilization. Humanity is no longer just surviving, it is shaping the destiny of worlds. As this long transformation continues, one question remains at the center of it all. Will Earth remain humanity's emotional home, or will it eventually become just one managed environment among many? As tens of millions of years pass, the long shadow of the Moon's disappearance becomes fully visible across Earth's destiny. By this stage, humanity is no longer merely adapting to change. It is actively choosing how to exist within a universe that no longer guarantees stability. The planet continues drifting through cycles of extreme axial tilt, volatile climate shifts, and geological transformation. Technology has kept civilization alive, but the question now becomes deeper. How long can Earth remain a viable home without the natural stabilizing forces that once protected it? Earth's climate cycles grow increasingly intense. Even with planetary engineering systems operating at maximum efficiency, the planet experiences periods of severe imbalance. During extreme tilt phases, polar regions receive direct sunlight for extended periods, turning once frozen landscapes into temporary oceans. Ice sheets collapse rapidly, releasing massive volumes of fresh water into the seas. This disrupts ocean salinity, weakens global circulation, and alters atmospheric pressure systems. When the tilt swings back, temperatures plunge. Newly melted oceans freeze again. Expanding ice sheets reflect sunlight, amplifying cooling effects. Storm systems intensify as temperature gradients sharpen. Hurricanes grow larger and more powerful. Dust storms spread across drying continents. The surface of Earth becomes a world of extremes. Planetary engineers struggle to maintain equilibrium. Climate regulation platforms operate constantly, adjusting radiation flow, atmospheric composition, and ocean circulation. Despite their sophistication, these systems face physical limits. Energy demands rise. Maintenance becomes increasingly complex. Small failures can cascade into large-scale disruptions. Human settlements adapt further. Surface cities become rare. Most populations now live underground, underwater, or in orbit. Subterranean habitats expand into entire continental networks, protected from temperature extremes and radiation fluctuations. These underground cities rely on artificial sunlight, geothermal energy, and closed-loop ecosystems to sustain life. Underwater habitats also become common. As sea levels fluctuate wildly, floating and submerged cities adjust position to remain within stable ocean zones. Advanced pressure-resistant structures house millions of people beneath the waves. where temperature remains more stable than on the surface. Orbital populations continue growing. Space habitats orbit Earth in dense networks connected by transportation corridors. These habitats serve as cultural centers, research hubs, and industrial complexes. Many citizens are now born in space and have never experienced Earth's surface environment. This shift transforms human identity. The concept of home becomes fluid. Some people identify as Earthborn, others as orbital citizens, others as interplanetary settlers. Cultural diversity expands beyond geography and into gravitational environments, atmospheric conditions, and habitat design. Education evolves to reflect this complexity. Children learn to operate in multiple environments. They are trained in orbital navigation, habitat maintenance, planetary science, and systems management. Knowledge becomes increasingly interdisciplinary, blending physics, biology, engineering, and social science. Human physiology also adapts further. Long-term exposure to artificial gravity environments and altered light cycles influences bone density, muscle structure, and circadian biology. Medical science develops techniques to preserve health across different gravitational conditions. Some populations choose permanent genetic modifications to optimize survival in specific habitats. As humanity becomes more technologically integrated, artificial intelligence systems play an even greater role. These systems coordinate planetary climate controls, orbital traffic, resource distribution, and disaster response. They predict long-term trends and propose optimization strategies. Human oversight remains essential, but AI becomes a critical partner in managing civilization. Despite technological progress, Earth's long-term outlook grows more uncertain. Geological changes accelerate under fluctuating climate stress. Increased erosion reshapes continents. River systems change course. Coastal landscapes are constantly rebuilt by rising and falling seas. Some regions become permanently unstable and are abandoned. Volcanic activity increases in certain zones due to changing stress patterns within Earth's crust. Large eruptions inject massive amounts of ash and gas into the atmosphere, temporarily overwhelming climate regulation systems. Emergency responses mitigate damage, but these events highlight Earth's unpredictable nature. Meanwhile, biodiversity continues evolving under constant environmental pressure. New species emerge that are highly adaptable, capable of surviving extreme temperature ranges and irregular seasons. However, overall biodiversity declines as specialized species disappear. Ecosystems become simpler, dominated by resilient generalists rather than complex interdependent networks. Humanity attempts to preserve endangered species through genetic archives and artificial habitats. Seed vaults store plant DNA. Cryogenic libraries preserve animal genetic material. Artificial ecosystems recreate extinct habitats in controlled environments. While these efforts maintain biological knowledge, they cannot fully replace natural ecosystems. Cultural memory of the moon becomes increasingly abstract. Only historical records and simulations preserve its image. Virtual reality recreations allow people to experience moonlit nights, eclipses, and tidal movements. Museums display holographic models of the ancient Earth-Moon system. Some cultural movements emerge dedicated to lunar remembrance. Annual global events commemorate the moon's role in shaping Earth's past. These events celebrate the stability it once provided and remind humanity of the fragile balance that allowed civilization to arise. Religion and philosophy continue evolving. Some belief systems emphasize acceptance of cosmic change, teaching that impermanence is a fundamental feature of reality. Others focus on humanity's responsibility to preserve life regardless of environmental instability. New ethical frameworks develop around planetary management and intergenerational responsibility. Political structures adapt again. Planetary governance becomes more centralized to manage climate regulation, space infrastructure, and disaster response. Regional autonomy still exists, but major decisions about Earth's survival are made collectively. International cooperation becomes less optional and more essential. Conflicts do not disappear entirely. Competition over orbital territory, energy resources, and technological control still arises. However, the shared risk of planetary collapse discourages large-scale warfare. Mutual dependence on global systems encourages negotiation and cooperation. At the same time, humanity's presence beyond Earth expands rapidly. Mars becomes increasingly self-sufficient. Terraforming efforts begin producing localized, breathable environments. Asteroid colonies grow into permanent settlements. Outer solar system habitats flourish around moons with abundant resources. This expansion creates an important strategic shift. Earth is no longer humanity's only lifeline. Civilization becomes distributed across multiple worlds and habitats. This reduces dependence on Earth's unstable environment and increases long-term survival chances. However, emotional attachment to Earth remains strong. Despite instability, Earth is still seen as humanity's birthplace. Cultural traditions, historical landmarks, and ancestral connections keep many people emotionally tied to the planet. Some movements advocate for preserving Earth at all costs, even if it requires extreme planetary engineering. Others argue that humanity should gradually transition away from Earth, allowing it to evolve naturally without constant intervention. These debates shape long-term policy. Should Earth remain a managed environment designed for human habitation? Or should humanity accept that Earth's natural evolution may make it less suitable for large populations, focusing instead on space-based civilization? As millions of years pass, Earth approaches critical thresholds. Extreme axial tilt phases become more frequent. Climate regulation systems strain under increasing demands. Geological instability grows. Scientists warn that maintaining surface habitability indefinitely may become impossible. This realization forces humanity to confront a difficult truth. The moon's disappearance initiated a process that cannot be fully reversed. Technology can slow Earth's destabilization, but it cannot restore the original cosmic balance that once existed. At this stage, humanity faces a defining decision: either invest unprecedented resources into full planetary stabilization, reshaping Earth's rotation, orbit, and mass distribution, or gradually transition civilization away from Earth, preserving it as a historical and ecological archive, rather than a primary home. This choice is not purely technical, it is emotional, cultural, and philosophical. It asks humanity to decide what home truly means. Is home a physical planet? Or is it the collective survival and continuity of intelligent life? As this debate unfolds, Earth continues its slow transformation. Seasons grow more extreme. Ice ages and heat eras alternate rapidly. The planet remains alive but increasingly unpredictable. In the next and final phase of this scenario, we will explore humanity's ultimate response, whether Earth becomes a fully engineered world, a protected natural relic, or a fading cradle of civilization, as humanity embraces life beyond its home planet. Because when the moon disappeared, it set humanity on a path that leads far beyond Earth itself. As the far future unfolds, humanity reaches a moment that no previous civilization has ever faced. Earth, once a naturally balanced world, now stands at the edge of its technological limits. The moon's disappearance has pushed the planet into an era where survival depends not on adaptation alone, but on deliberate choice. Civilization must decide what Earth will become. By this time, Earth's axial instability reaches levels that strain even the most advanced climate control systems. Extreme tilt cycles arrive more frequently. Temperature differences between hemispheres grow sharper. Ice ages and heat eras no longer take tens of thousands of years to develop. They unfold within centuries, sometimes faster. This rapid oscillation leaves little time for ecosystems or infrastructure to recover. Planetary engineers present bold proposals. One option is full-scale stabilization, reshaping Earth's rotational dynamics using massive orbital structures. These systems would act as artificial gravitational anchors, applying controlled forces to slow axial drift and reduce tilt fluctuations. The scale of such projects is unprecedented. Entire asteroid-sized masses would be repositioned in orbit. Energy requirements would exceed anything humanity has ever attempted. Another option is partial stabilization. Instead of fully correcting Earth's motion, technology could maintain habitable zones around the equator and mid-latitudes. Climate control systems would focus on protecting specific regions where most of the population lives. Other areas would be allowed to evolve naturally, becoming wild zones shaped by extreme climate cycles. The third option is gradual departure. Humanity could accept that Earth's natural stability is permanently lost and shift the center of civilization into space. Earth would become a preserved world maintained as a biological archive and cultural heritage site rather than a primary habitat. Each option carries profound consequences. Full stabilization would transform Earth into a fully engineered planet. Gravity manipulation systems, orbital mass regulators, and continuous climate control would redefine what a planet can be. Earth would no longer be governed primarily by natural forces. It would become a constructed environment maintained by intelligent life. However, this approach carries risk. Artificial stabilization systems must operate flawlessly for millions of years. Any large-scale failure could trigger catastrophic consequences. Critics argue that placing Earth's survival entirely in technological hands introduces vulnerability on an unprecedented scale. Partial stabilization offers a compromise. Humanity preserves livable regions while allowing the rest of the planet to evolve naturally. This reduces engineering demands and risk, but creates inequality. Some regions would remain stable and prosperous, while others become increasingly uninhabitable. Ethical questions arise about who gets to live in protected zones and who does not. Gradual departure represents the most radical shift. Humanity would expand permanently into orbital habitats, Mars colonies, and artificial worlds. Earth would remain important symbolically, but no longer serve as civilization's foundation. Supporters of this approach argue that diversification increases survival odds and reduces dependence on one unstable planet. These debates dominate politics, culture, and philosophy. Entire generations grow up during this decision-making era. Schools teach planetary ethics alongside science. Citizens participate in global referendums about Earth's future. Artists create works exploring humanity's relationship with its birthplace. As discussions continue, Earth does not pause. Geological processes continue reshaping the surface. Mountain ranges erode faster under extreme weather. River systems change direction. Volcanic activity fluctuates unpredictably. Coastal regions rise and fall with repeated sea level shifts. Biodiversity declines further in uncontrolled zones. Many species survive only in protected reserves and artificial ecosystems. Genetic libraries expand, preserving the biological record of Earth's evolutionary history. Scientists maintain living archives of plants and animals in climate-controlled environments. Despite environmental instability, human culture flourishes in new forms. Orbital cities develop unique traditions. Space-borne communities celebrate different holidays tied to orbital cycles instead of seasons. Music, art, and language evolve across different habitats, creating a multi-environment civilization. Human psychology adapts as well. People grow accustomed to living in artificial environments. Sky projections replace natural horizons. Simulated weather provides emotional comfort. Virtual reality experiences recreate Earth's ancient landscapes, including forests, oceans, and moonlit nights. Some communities choose to live in controlled heritage zones on Earth, preserving natural landscapes as closely as possible to their original state. These zones become pilgrimage destinations where people experience Earth's remaining wild beauty. Technological progress accelerates as humanity prepares for whichever path it chooses. Energy generation reaches extraordinary levels through fusion reactors and space-based solar collectors. Material science develops ultra-strong structures capable of withstanding planetary-scale forces. Artificial intelligence systems simulate millions of future scenarios to guide decision-making. As centuries pass, the balance slowly shifts toward a hybrid solution. Humanity realizes that no single option provides complete security. Instead, civilization adopts a multi-layered strategy. Earth receives partial stabilization. Key regions are protected and climate regulated to preserve long-term habitability. Large-scale gravitational stabilization projects are implemented gradually, reducing axial drift without fully reshaping Earth's dynamics. At the same time, humanity continues expanding into space, reducing dependence on Earth. This approach spreads risk. If Earth becomes more unstable than expected, off-world populations provide continuity. If space habitats face challenges, Earth remains a cultural and biological anchor. Implementation begins with enormous construction projects. Orbital mass regulators are assembled using asteroid materials. Climate control platforms expand in orbit. Ocean circulation systems are upgraded. Underground cities expand further to protect populations from surface instability. Humanity enters an era of planetary-scale engineering unlike anything before. The planet becomes a living experiment in long-term environmental management. Scientists monitor feedback loops continuously, adjusting systems to prevent runaway effects. At the same time, cultural emphasis shifts towards intergenerational responsibility. Decisions are no longer made for short-term political gain. Policies are evaluated based on impacts thousands of years into the future. This shift transforms governance structures and leadership priorities. Despite progress, uncertainty remains. Earth's natural evolution cannot be fully controlled. Unexpected events still occur. Asteroid impacts, volcanic supereruptions, and solar activity fluctuations challenge planetary systems. Humanity remains vigilant, constantly adapting strategies. Yet something remarkable emerges from this struggle. Humanity develops a deeper understanding of planetary systems than ever before. Knowledge gained from stabilizing Earth allows scientists to terraform barren worlds more effectively. Mars becomes increasingly habitable. Artificial worlds flourish across the solar system. Earth's role evolves into that of a central cultural world, rather than the sole home of humanity. It becomes a place of memory, origin, and symbolic importance. People travel to Earth not only to live, but to reconnect with humanity's roots. As the far future continues, Earth stands transformed. It is no longer the untouched cradle of life it once was. It is a hybrid world, part natural, part engineered, shaped by billions of years of evolution and millions of years of intelligent intervention. The disappearance of the Moon becomes a defining event in cosmic history. It marks the moment when humanity was forced to take responsibility for planetary stability. It pushed civilization beyond passive existence into active planetary stewardship. In the end, Earth does not disappear. It changes. Humanity does not vanish. It evolves. The Moon's absence taught civilization a powerful lesson. Stability is not permanent, but survival is possible when intelligence, cooperation, and long-term thinking guide action. And as humanity continues spreading through the cosmos, carrying Earth's legacy beyond its original home, the story of the lost moon becomes more than a tragedy. It becomes the moment when a species learned to shape its own destiny among the stars. As millions of years continue to unfold, humanity enters a phase where survival is no longer defined by crisis management, but by long-term cosmic strategy. Earth, reshaped by the moon's disappearance and centuries of planetary engineering, now exists as a carefully balanced world suspended between natural evolution and technological control. Civilization has stabilized the planet enough to prevent total collapse, but the deeper question remains: what is humanity's ultimate place in the universe? By this era, Earth's surface is divided into distinct zones. Stabilized regions near the equator and mid-latitudes remain habitable through continuous climate regulation. These zones contain most remaining surface ecosystems and heritage landscapes preserved from Earth's ancient past. Extreme climate zones closer to the poles are largely abandoned or converted into research territories where scientists study planetary evolution under harsh conditions. Underground megacities dominate human population centers. These vast networks stretch beneath continents, connected by high-speed transit tunnels and energy distribution corridors. Inside these cities, artificial skies simulate day and night cycles. Climate-controlled parks provide green spaces. Entire ecosystems exist within sealed environments, allowing humans to experience nature even as the surface world becomes increasingly unpredictable. Orbital habitats continue expanding. Some orbit Earth closely, acting as extensions of planetary infrastructure. Others exist farther away, forming independent city-states in space. These habitats differ in design depending on cultural preferences. Some prioritize Earth-like gravity and atmosphere. Others experiment with lower gravity environments optimized for manufacturing or scientific research. Human civilization now exists across multiple layers: surface Earth, underground Earth, orbital space, and off-world colonies. This layered existence reshapes identity. People no longer define themselves solely by nationality or geography, but by habitat type and environmental background. New cultural groups emerge based on life in gravity habitats, deep underground cities, or artificial worlds. Economies adapt to this complexity. Resource extraction shifts heavily towards space. Asteroids provide metals, rare elements, and construction materials. Solar energy collected in orbit supplies power to Earth and space settlements alike. Earth itself becomes less exploited for raw materials, preserving remaining ecosystems and geological stability. Education evolves to prepare citizens for multi-environment life. Students learn orbital navigation, habitat maintenance, environmental engineering, and planetary ethics. Knowledge is no longer focused only on Earth-based survival, but on sustaining civilization across multiple worlds. Medical science also transforms. Humans adapt biologically and technologically to different environments. Some populations undergo genetic modifications to improve bone density retention in low gravity. Others enhance radiation resistance for life in space habitats. Advanced medical implants regulate internal biological processes, allowing humans to thrive in artificial conditions. Despite these advancements, Earth's emotional importance remains strong. It is still viewed as humanity's birthplace, the origin of culture, language, and history. Pilgrimages to preserved natural zones become common. People travel to experience forests, oceans, and mountain landscapes maintained as closely as possible to their ancient states. These heritage zones are protected by international agreements. Strict regulations limit industrial activity. Advanced monitoring systems track environmental health and prevent unauthorized interference. Earth's remaining natural beauty becomes one of civilization's most valuable treasures. Meanwhile, the memory of the moon continues fading from lived experience. Only historical records and simulations preserve its presence. New generations grow up knowing the moon only as a concept rather than a visible object in the sky. Lunar stories become myth-like, blending science with legend. Cultural movements emerge focused on cosmic memory. Museums create immersive experiences that allow people to walk through recreated moonlit nights, witness tidal movements, and observe ancient eclipses. These experiences preserve humanity's emotional connection to the lost moon and Earth's former stability. Philosophy evolves in response to humanity's expanded existence. Thinkers debate whether humans should continue reshaping planets or accept natural cosmic evolution. Some argue that humanity has become a planetary engineer species with a responsibility to stabilize worlds. Others believe that excessive control risks creating fragile artificial systems dependent on constant maintenance. Religion adapts again. Some belief systems reinterpret creation stories to include humanity's role as a caretaker of worlds. Others emphasize humility in the face of cosmic forces. New spiritual movements emerge that focus on interconnectedness across planets and habitats. Political structures shift toward multi-world governance. Earth-based governments coordinate with orbital and off-world councils. Decision-making becomes distributed across habitats while maintaining shared planetary goals. New laws regulate space expansion, resource extraction, and environmental protection across multiple worlds. Security concerns also evolve. Protecting planetary infrastructure becomes critical. Defense systems monitor space for potential threats such as asteroids or hostile activity. Cybersecurity protects planetary climate networks from sabotage. Redundant control systems prevent single points of failure. As humanity becomes increasingly decentralized, resilience improves. Civilization no longer depends solely on Earth's stability. If one habitat fails, others continue functioning. This redundancy marks a turning point in species survival strategy, yet Earth's natural evolution continues. Despite stabilization efforts, slow geological processes reshape continents. Mountain ranges erode, new volcanic islands form, ocean basins shift. Earth remains a living planet, not a static monument. Climate regulation systems adapt continuously. Engineers refine algorithms to manage atmospheric composition, ocean circulation, and energy balance. These systems grow more sophisticated, learning from centuries of operation. They predict potential instability years in advance and adjust conditions gradually to prevent abrupt changes. Despite all precautions, unexpected events still occur. Solar storms disrupt communication networks. Large volcanic eruptions temporarily overwhelm atmospheric control systems. Rare asteroid impacts test planetary defense networks. Each crisis reinforces the importance of preparedness and adaptability. Human culture responds by valuing resilience as a core principle. Stories, art, and education emphasize survival through cooperation and innovation. Hero figures are no longer warriors or rulers, but engineers, scientists, and environmental guardians who protect planetary systems. As centuries turn into millions of years, humanity's long-term planning horizon expands further. Scientists begin modeling Earth's evolution tens of millions of years into the future. They study how axial instability might continue increasing, and whether artificial stabilization can remain effective indefinitely. Some models suggest that Earth will eventually reach conditions where maintaining surface habitability becomes increasingly expensive and complex. At that point, humanity may face another major transition, shifting most of its population permanently off Earth. This possibility sparks intense debate. Some believe Earth should always remain central to civilization, regardless of difficulty. Others argue that clinging to Earth out of nostalgia limits humanity's future potential. As discussions continue, Earth stands at the center of a growing interplanetary civilization. It remains symbolically powerful, culturally rich, and scientifically valuable, but it is no longer humanity's only anchor. The moon's disappearance, once seen as a disaster, has transformed into a catalyst for expansion, innovation, and cosmic awareness. Humanity has learned to survive without relying on natural stability alone. It has learned to build stability through intelligence and cooperation. Yet the story is not complete. Earth's future remains uncertain. The universe continues changing. new challenges will arise. New discoveries will reshape understanding. In the final phase of this journey, we will look beyond Earth itself, toward the ultimate fate of a moonless planet and the long-term destiny of humanity as a species no longer bound to a single world. Because the disappearance of the moon did not end Earth's story, it expanded it into something far larger than anyone could have imagined. As the deepest future unfolds, humanity reaches the final stage of its transformation from a planetary species into a fully cosmic civilization. Earth, shaped by millions of years of adaptation and engineering, stands as both a monument to humanity's origins and a living laboratory of planetary management. The moon's disappearance, once seen as a catastrophe, now marks the beginning of this long evolutionary journey. By this era, Earth's stabilization systems operate with extraordinary precision. Orbital climate regulators, atmospheric processors, and ocean circulation networks work together as a single planetary organism. Artificial intelligence systems continuously adjust thousands of variables to maintain habitable conditions in protected regions. These systems predict environmental shifts decades in advance, allowing gradual corrections rather than emergency responses. However, even with this advanced control, Earth remains a dynamic planet. Geological activity continues. Continents drift slowly. Mountain ranges rise and erode. Volcanoes occasionally reshape landscapes. Climate regulation systems account for these changes, but cannot eliminate them entirely. Earth remains alive, not frozen in time. Human populations on Earth become smaller relative to off-world settlements. Most people now live in orbital habitats, Mars colonies, and artificial worlds constructed throughout the solar system. Earth serves primarily as a cultural centre, research hub, and biological archive rather than the main population base. Large regions of Earth are designated as planetary preserves. These areas protect remaining natural ecosystems and geological landmarks. Strict regulations limit human activity to minimize environmental stress. Scientists study these preserves to understand natural planetary processes in a controlled environment. Urban centers on Earth are designed for minimal environmental impact. Buildings integrate seamlessly with surrounding landscapes. Energy comes entirely from renewable and fusion sources. Waste is recycled through closed-loop systems. Human presence becomes lighter, more respectful of planetary balance. Meanwhile, humanity's off-world expansion accelerates. Terraforming projects on Mars reach advanced stages. Artificial oceans, controlled atmospheres, and engineered ecosystems transform once barren landscapes into habitable environments. Outer solar system habitats flourish around resource-rich moons and asteroids. Space infrastructure becomes increasingly interconnected. Transport corridors link Earth, Mars, and orbital habitats. Massive space stations function as trade hubs and research centers. Communication networks transmit information instantly across vast distances. Human identity evolves further. People no longer define themselves by planet of birth alone. Cultural identity becomes multi-planetary. Some families trace their heritage across different worlds. Children grow up experiencing multiple environments throughout their lives. Education systems emphasize adaptability and exploration. Students train in planetary science, astrophysics, habitat engineering, and cosmic navigation. Knowledge becomes oriented toward long-term survival across diverse environments. Medical science advances to support long-duration space living. Artificial organs, regenerative medicine, and nanotechnology allow humans to survive radiation exposure, microgravity, and extreme conditions. Life expectancy increases dramatically. Some individuals live for centuries through advanced medical treatments. As humanity spreads, philosophical perspectives shift. The idea of Earth as the center of existence fades. Instead, Earth becomes one important world among many. However, its emotional significance remains powerful. It is remembered as the birthplace of human culture and history. The moon's disappearance becomes a foundational event in historical education. It is taught as the moment humanity realized that planetary stability is temporary. Students learn how this event forced civilization to develop planetary engineering, space expansion, and long-term thinking. Cultural institutions preserve the memory of Earth's ancient sky. Virtual reality archives allow people to experience moonlit nights, eclipses, and tidal oceans as they once existed. These experiences become symbolic of humanity's fragile beginnings. Religion and philosophy continue evolving. Some belief systems emphasize humanity's role as a cosmic steward, responsible for protecting life wherever it exists. Others focus on the humility required to coexist with vast cosmic forces. New ethical frameworks emerge around terraforming, artificial life creation, and planetary management. Political structures expand into multi-system governance. Councils represent populations across Earth, Mars, orbital habitats, and distant colonies. Decision-making becomes complex but necessary to coordinate shared resources and security. Defense systems protect civilization from external threats. Planetary defense networks monitor near-Earth space for asteroids. Interplanetary patrols safeguard transport corridors. Cybersecurity protects infrastructure controlling planetary systems. Despite these advancements, uncertainty remains. The universe is not static. Solar evolution, cosmic radiation, and gravitational interactions continue shaping planetary systems. Humanity must remain adaptable to survive. Scientists begin modelling even longer-term futures. They study how the sun's increasing brightness will eventually threaten Earth and inner solar system habitats. Plans are developed to gradually relocate civilization outward as conditions change. Some long-term projects explore starship construction and interstellar travel. Humanity prepares for the possibility that one day it may leave the solar system entirely. Knowledge gained from surviving Earth's instability becomes invaluable for adapting to other star systems. Earth, in this far future, becomes a symbol of humanity's first great challenge and first great success. It represents the moment when civilization learned to survive without relying solely on natural stability. As centuries turn into tens of millions of years, Earth's role continues evolving. It remains inhabited but not crowded. It becomes a world of research, memory, and ecological preservation. Off-world colonies become the main drivers of population growth and innovation. The moon's absence is no longer felt emotionally. It exists only in records and simulations. New generations know the moon as history rather than experience, yet its legacy lives on in the technologies and cultural shifts it inspired. In the end, Earth does not fade into irrelevance. It transforms. It becomes a living museum of humanity's origins and a reminder of how fragile planetary stability truly is. The disappearance of the moon forced humanity to grow beyond planetary dependence. It taught civilization to think on cosmic timescales, to engineer environments responsibly, and to prepare for a future beyond any single world. And as humanity continues its journey through the universe, carrying Earth's history and lessons with it, one truth remains clear: the loss of the moon did not end life on Earth. It changed it forever. It turned a fragile planetary species into a cosmic civilization, and it marked the moment humanity learned to survive, not because the universe was stable, but because intelligence chose to adapt. As the farthest eras of Earth's future arrive, the planet exists in a quiet but profound state of transformation. Civilization has moved beyond the urgency of survival and into the responsibility of legacy. Humanity now thinks not only about living, but about what should be preserved, remembered, and carried forward into the deep future. Earth's surface is no longer dominated by sprawling cities or industrial zones. Instead, it is shaped by carefully planned preservation regions, research landscapes, and cultural sanctuaries. Vast areas of the planet are allowed to evolve naturally under controlled conditions, monitored by planetary systems that ensure ecosystems do not collapse completely. Forests grow and recede with climate cycles. Oceans remain biologically active through artificial circulation networks. Ice caps expand and contract without threatening global catastrophe. Human presence on Earth becomes subtle and intentional. Small communities inhabit surface settlements designed to blend with natural environments. These communities focus on ecological research, planetary history preservation, and cultural continuity. Life on Earth becomes less about mass population and more about stewardship. The majority of humanity now lives beyond Earth. Orbital habitats form immense networks around the planet, connected by transportation corridors and energy exchange systems. Mars has developed into a semi-terraformed world with breathable regions, controlled oceans, and stable agricultural zones. Further out, artificial habitats orbit gas giants and resource-rich asteroids, forming independent societies. This multi-world civilization changes how humans understand belonging. People no longer see themselves as citizens of a single planet, but as participants in a shared cosmic civilization. Identity becomes shaped by experience rather than location. Some individuals live on Earth for a period, then move to orbital habitats, then settle on Mars or artificial worlds. Life becomes a journey across environments. Education reflects this mobility. Children are trained to adapt to multiple gravity levels, atmospheric conditions, and cultural systems. Learning emphasizes flexibility, cooperation, and planetary awareness. Students study Earth's history not as distant facts, but as a living lesson in planetary vulnerability and resilience. The Moon's disappearance becomes one of the most significant historical events taught across all educational systems. It is remembered as the moment humanity was forced to confront the reality that no planetary system is permanent. It marks the transition from natural dependence to technological responsibility. Cultural institutions preserve Earth's ancient past. Massive digital archives store records of ecosystems, civilizations, languages, and art. Virtual reality environments recreate Earth's early landscapes, including oceans shaped by lunar tides and skies illuminated by moonlight. These experiences allow future generations to understand what was lost and what was gained. Art evolves to reflect humanity's expanded perspective. Creative expression no longer focuses only on local experiences, but on cosmic themes, the passage of time, the evolution of planets, and the fragility of life. Music incorporates frequencies inspired by planetary vibrations and orbital rhythms. Visual art blends natural and artificial aesthetics, symbolizing the fusion of biology and technology. Religion and philosophy also mature. Many belief systems shift from focusing on individual salvation to collective responsibility. The idea of planetary guardianship becomes central. Some philosophies emphasize humility in the face of cosmic forces. Others celebrate humanity's ability to shape environments while warning against arrogance. Ethical debates grow more complex. Questions arise about how much intervention is acceptable when managing planets. Should ecosystems be preserved exactly as they once were, or allowed to evolve naturally? Should humanity terraform new worlds or leave them untouched? These debates influence policy and cultural norms across civilizations. Governance becomes increasingly decentralized but coordinated. Planetary councils represent Earth, Mars, orbital habitats, and distant colonies. Decision-making relies on long-term projections rather than short-term political cycles. Leaders are evaluated based on sustainability metrics and intergenerational impact. Advanced artificial intelligence systems assist in governance, modeling future scenarios and predicting the consequences of large-scale decisions. However, humans retain final authority, ensuring ethical considerations remain central. Earth's role in this multi-world civilization becomes symbolic and scientific. It serves as the reference point for planetary management practices. Lessons learned from stabilizing Earth inform terraforming projects elsewhere. Earth becomes the training ground for planetary engineers who later work on other worlds. Scientists continue monitoring Earth's long-term evolution. They track axial tilt changes, geological shifts, and climate cycles. Despite stabilization efforts, Earth remains dynamic. Slow changes continue shaping continents and ecosystems. The planet is alive, evolving alongside humanity. Some scientists propose a final stabilization project, a complete rebalancing of Earth's rotation and mass distribution to permanently reduce axial instability. This project would involve repositioning massive orbital structures and redistributing planetary mass using advanced technology. While technically possible, it remains controversial. Supporters argue that permanent stabilization would protect Earth for billions of years, preserving it as a stable home and ecological archive. Opponents warn that such deep intervention could produce unforeseen consequences and remove Earth's natural evolutionary processes. As debates continue, humanity chooses caution. Instead of forcing permanent stabilization, civilization maintains adaptive control systems that respond to changes without fully overriding natural processes. Earth remains partially natural, partially engineered, a hybrid planet reflecting humanity's evolving philosophy. Meanwhile, exploration beyond the solar system begins in earnest. Interstellar probes and early starships are launched toward nearby star systems. These missions carry biological samples, cultural archives, and autonomous ecosystems designed to establish life beyond the sun's influence. Humanity prepares for a future where it is no longer bound to one star. Knowledge gained from surviving Earth's instability becomes essential for adapting to alien planetary systems. Earth's importance remains emotional and historical. It is the birthplace of language, art, science, and civilization. It is where humanity learned to survive planetary instability and evolve beyond natural dependence. Ceremonial events commemorate key moments in Earth's history, including the Moon's disappearance. These events honor past generations who lived through the transition and laid the foundation for cosmic civilization. Despite the passage of millions of years, Earth remains recognizable in spirit. Oceans still shimmer under artificial skies. Forests grow in preserved regions. Mountains rise and erode. The planet continues telling its story, shaped by both nature and intelligence. Humanity, now spread across multiple worlds, carries Earth's legacy forward. Cultural traditions reference Earth as the origin of humanity's values and identity. Even distant colonies maintain symbolic connections through shared history and commemorative rituals. In this far future, the Moon's absence is no longer felt as loss. It is understood as transformation. What once seemed like disaster became a turning point that forced humanity to mature as a species. The disappearance of the Moon taught civilization that stability is not guaranteed, but adaptation is possible. It showed that survival depends not only on technology, but on cooperation, ethical responsibility, and long-term thinking. Earth's story continues, not as a static world, but as a living chapter in humanity's cosmic journey. And as humanity looks outward towards distant stars, carrying the memory of its first home, it does so with the understanding that every world is temporary, but the pursuit of life and knowledge can endure far beyond any single planet. As the final deep eras unfold, Earth enters a stage where time itself becomes the dominant force shaping the planet and civilization. Millions upon millions of years have passed since the Moon vanished, and humanity now exists as an ancient, multi-world species with memory stretching across geological ages. Earth, though still alive and carefully managed, is no longer the center of survival. Instead, it has become a symbol of origin, endurance, and transformation. The sun slowly grows brighter as it ages, a process that scientists predicted long ago. This gradual increase in solar output places new pressure on Earth's climate systems. Even with orbital reflectors and atmospheric regulation, maintaining surface habitability becomes increasingly difficult. Temperature control systems must operate constantly to prevent runaway warming. Ocean cooling networks intensify to protect marine ecosystems. Polar ice reserves shrink despite artificial stabilization. In response, humanity adjusts Earth's role once again. Large populations relocate permanently to orbital habitats and outer solar system settlements, where environmental control is easier and solar intensity is lower. Earth transitions further into a protected planetary reserve, a world maintained for research, culture, and historical preservation rather than mass habitation. The surface of Earth becomes quieter. Cities shrink into research centers and heritage communities. Vast areas are designated as ecological sanctuaries where artificial intervention is minimized. These regions allow scientists to observe long-term planetary evolution under semi-natural conditions, offering insight into how planets change when guided gently rather than fully controlled. Underground and underwater habitats remain active, housing specialists responsible for planetary maintenance and research. These communities become guardians of Earth's systems, monitoring atmospheric composition, tectonic activity, and ocean circulation. Their work ensures Earth does not collapse into environmental chaos, even as natural forces intensify. Cultural life on Earth becomes deeply reflective. People who choose to live on the planet do so not for convenience, but for connection. They come to experience Earth's landscapes, preserved forests, ancient oceans, and geological monuments. Life on Earth becomes a form of pilgrimage rather than ordinary residence. Education centers on Earth teach planetary history in immersive ways. Students walk through reconstructed ancient environments using advanced simulation technology. They experience pre-moon disappearance Earth, moonlit nights, tidal coastlines, and early human civilizations. These lessons emphasize the fragility of planetary stability and the responsibility of intelligent species. Meanwhile, humanity's presence beyond Earth continues expanding. Mars becomes fully self-sustaining. Artificial worlds orbit distant planets. Settlements form around icy moons rich in water resources. Humanity builds habitats designed to last millions of years, protected from radiation and cosmic hazards. Interstellar exploration accelerates. Long-duration starships travel toward nearby star systems, carrying autonomous ecosystems and genetic archives. These missions are slow, measured in centuries and millennia, but humanity now thinks on such timescales. The goal is not conquest, but survival and continuity of life. As humanity spreads further, Earth's symbolic importance grows stronger. It becomes known as the First World, the place where civilization learned to survive planetary instability. Ceremonial traditions honor Earth's role in shaping human values and identity. Global archives preserve Earth's complete biological and cultural record. Every known species, language, and historical artifact is digitally stored and physically preserved in secure facilities. These archives ensure that even if Earth's environment eventually becomes uninhabitable, its legacy will endure. Philosophy evolves again. Thinkers debate whether Earth should remain partially natural or be fully engineered to withstand the sun's increasing brightness. Some argue that Earth should be preserved as a living museum, allowing natural evolution to continue even if it eventually becomes hostile to human life. Others believe Earth should be fully transformed into a controlled habitat, capable of supporting life indefinitely. The compromise remains consistent with earlier decisions. Humanity continues adaptive management rather than absolute control. Earth is protected, stabilized where necessary, but not frozen in artificial perfection. The planet remains dynamic, evolving under gentle guidance rather than total domination. As centuries pass, Earth's ecosystems change further. Tropical zones shift poleward. Some species migrate toward cooler regions. Others adapt genetically to higher temperatures. Artificial habitats preserve vulnerable species and reintroduce them into protected zones when conditions allow. Oceans continue producing oxygen and regulating climate through artificial circulation systems. Coral ecosystems are preserved in controlled marine sanctuaries. Large marine reserves protect biodiversity and stabilize food webs. Geological activity persists. Continents slowly drift. Mountain ranges erode and reform. Volcanic eruptions occasionally reshape landscapes. Planetary systems adjust continuously, balancing natural processes with technological intervention. Human culture becomes deeply time-aware. People measure life not only in years, but in planetary cycles and stellar evolution phases. Festivals celebrate cosmic milestones such as solar brightness thresholds, orbital anniversaries, and interstellar mission launches. Art reflects this cosmic awareness. Music incorporates rhythms based on orbital mechanics. Visual art portrays humanity's journey from earthbound species to cosmic civilization. Literature explores themes of impermanence, memory, and intergenerational responsibility. Religion and spirituality emphasize continuity rather than permanence. Many belief systems teach that worlds rise and fall, but life and consciousness persist through adaptation. The moon's disappearance becomes a central metaphor for transformation rather than loss. Governance structures now operate across planetary and interstellar scales. Councils coordinate Earth preservation, solar system management, and interstellar expansion. Decision-making prioritizes long-term stability over short-term benefit. Artificial intelligence continues assisting in managing complex systems, but human values remain central. Ethical oversight ensures that technological power does not override respect for life and natural processes. As Earth approaches conditions where surface habitability becomes increasingly difficult due to solar evolution, humanity prepares for the eventual transition. Plans are developed to move most remaining populations permanently off Earth while maintaining a minimal caretaker presence. This transition is not seen as abandonment, but as evolution. Earth will continue existing as a living planet, even if humans no longer inhabit it extensively. Automated systems will maintain climate regulation and ecological balance as long as possible. The idea of Earth as a home transforms into Earth as an origin world, a place remembered, respected, and preserved, even if humanity's main populations move beyond it. In this far future, the moon's disappearance is no longer seen as the beginning of disaster. It is remembered as the first test that forced humanity to think beyond planetary dependence. It shaped the civilization that would eventually carry life beyond the sun. As humanity stands on the edge of interstellar existence, Earth remains behind as a quiet witness to billions of years of evolution and millions of years of intelligent stewardship. Oceans still move, winds still blow, mountains still rise and fall. The planet continues its story, even as humanity writes new chapters among the stars. The moon is gone, Earth is changed, humanity is transformed, and the universe continues expanding, offering new worlds, new challenges, and new possibilities for a species that learned how to survive when its oldest companion disappeared. As the deepest future stretches forward, Earth enters what scientists and historians call the Quiet Era. It is not an age of collapse, nor one of explosive growth. It is an era defined by balance, memory, and long-term stewardship. Humanity has matured beyond crisis-driven survival, and now exists as a civilization that understands how fragile planetary systems truly are. By this time, Earth's surface is largely preserved rather than exploited. Massive ecological corridors connect protected regions across continents. These corridors allow species to migrate naturally in response to climate shifts, maintaining genetic diversity and ecosystem resilience. Forests, wetlands, grasslands, and marine reserves form a planetary network designed to keep Earth biologically alive even as conditions slowly evolve. Artificial climate control systems continue operating, but in a reduced and refined role. Instead of forcing stability everywhere, they focus on preventing extreme runaway scenarios. Heat waves are softened, polar ice loss is slowed, ocean circulation is maintained at levels that preserve oxygen distribution and nutrient flow. Earth is no longer perfectly stable, but it is no longer in danger of rapid collapse either. Human presence on the planet becomes rare and deliberate. Most inhabitants are scientists, historians, planetary engineers, and caretakers. Their role is not to dominate the environment, but to observe, preserve, and guide Earth's slow evolution. These caretakers live in small, self-sustaining settlements designed to leave minimal ecological footprints. Life on Earth becomes quieter. Without dense cities and constant industrial activity, natural soundscapes return. Wind moves freely through forests. Ocean waves dominate coastlines. Animal populations recover in many preserved regions. Earth slowly regains aspects of its ancient wilderness, though shaped by artificial boundaries and monitoring systems. Meanwhile, humanity's main populations now exist beyond Earth. Orbital megastructures house billions. Mars has become a thriving world with controlled oceans and stable agricultural regions. Artificial habitats orbit distant planets, forming networks of independent civilizations connected by high-speed communication and transport systems. Interstellar settlements begin to appear. Early starship colonies establish footholds around nearby stars. These colonies carry Earth's biological archives and cultural heritage, ensuring continuity of life beyond the solar system. Humanity becomes truly multistellar. Despite this expansion, Earth remains central in a symbolic sense. It is recognized as the origin of humanity's values, science, and identity. Every major civilization across the stars traces its heritage back to Earth. Cultural traditions reference Earth as the first garden, the place where intelligent life learned to care for a planet. Education across all colonies includes Earth history as a core subject. Students learn about ancient oceans shaped by lunar tides, early civilizations guided by moonlight, and the turning point when the moon disappeared. This history is taught not as tragedy, but as transformation. The moon's disappearance becomes a defining lesson about impermanence. It teaches that even the most familiar cosmic structures can vanish. This awareness shapes how humanity treats new worlds. Terraforming projects become more cautious. Ecosystem preservation becomes a priority. Colonies are designed with redundancy and adaptability in mind. Philosophy reaches new depths. Thinkers debate humanity's role in the universe. Some argue that humanity has become a guardian species, responsible for preserving life wherever it emerges. Others emphasize coexistence rather than control, encouraging civilizations to adapt to planetary conditions rather than reshape them entirely. Ethical frameworks expand to include planetary rights. Some cultures recognize planets as entities with intrinsic value beyond their usefulness to intelligent life. Earth becomes the first world officially granted planetary protection status, ensuring it is preserved regardless of economic or strategic considerations. Governance structures reflect this philosophy. Earth preservation councils oversee planetary management, ensuring decisions prioritize long-term ecological health rather than short-term convenience. These councils include representatives from Earth-based caretakers, orbital populations, and interstellar colonies, ensuring diverse perspectives guide planetary stewardship. Artificial intelligence continues assisting with planetary monitoring. These systems track atmospheric chemistry, ocean health, biodiversity trends, and geological activity. They alert caretakers to potential threats and recommend intervention strategies when necessary. Despite technological sophistication, Earth remains unpredictable. rare events still occur. Supervolcanic eruptions reshape landscapes. Asteroid impacts occasionally strike remote regions. Solar storms disrupt magnetic field stability. Each event becomes a learning opportunity, refining humanity's understanding of planetary resilience. Human culture adapts to long-term thinking. Short-term trends lose importance. Societies measure success by centuries of stability rather than years of profit. Architecture is designed to last thousands of years. Infrastructure projects are evaluated based on generational impact. Art reflects this extended perspective. Sculptures are built to erode naturally over millennia, symbolizing the passage of time. Music compositions span hours or days, mirroring slow planetary rhythms. Literature explores stories that unfold across generations. Religion and spirituality continue evolving. Many belief systems emphasize continuity of life rather than permanence of form. The moon's disappearance becomes a spiritual symbol of cosmic change, reminding humanity that nothing remains fixed forever. Ceremonial events commemorate Earth's major evolutionary milestones. One of the most significant is the Lunar Transition Day, marking the moment when the moon vanished and humanity began its journey toward planetary stewardship and cosmic expansion. These ceremonies emphasize unity across worlds and habitats. As Earth continues aging alongside the Sun, scientists prepare for even more distant futures. Models predict that in hundreds of millions of years, solar radiation will push Earth beyond comfortable surface temperatures, even with artificial regulation. Plans are developed to gradually reduce human dependence on Earth's surface environments. Automated caretaking systems are upgraded to maintain Earth's ecosystems long after large-scale human presence ends. These systems are designed to operate autonomously, powered by renewable and fusion energy, preserving planetary balance for as long as possible. Earth slowly transitions into a world primarily maintained by machines and small caretaker communities. Its role becomes that of a living archive, a preserved example of a once naturally stable planet that evolved under intelligent guidance. Humanity's emotional connection to Earth remains strong, even as populations move farther away. Long-distance communication networks allow people across star systems to experience Earth's seasons, weather patterns, and environmental changes in real time through immersive observation platforms. People gather virtually to watch storms roll across preserved oceans or witness the slow movement of glaciers. Earth becomes a shared cultural reference point for a civilization spread across space. In this far future, humanity no longer fears planetary instability. It understands it. It plans for it. It adapts to it. The moon's absence is no longer viewed as loss. It is recognized as the moment that forced humanity to evolve beyond passive existence. It taught civilization to protect, preserve, and adapt. Earth stands quietly beneath artificial skies and natural stars, shaped by billions of years of natural evolution and millions of years of intelligent care. It is no longer the center of civilization, but it remains the heart of humanity's story. And as humanity continues exploring the universe, carrying Earth's lessons across the stars, the planet remains behind as a silent witness, a reminder of where it all began and how far life has come since. The night the moon disappeared, as the last great chapter of Earth's moonless story unfolds, time itself becomes the dominant force shaping both the planet and humanity's destiny. Billions of years have passed since the moon vanished. The sun has grown brighter and larger, its slow transformation altering the balance of the entire solar system. Earth now exists in a delicate state, preserved not by natural stability, but by the combined effort of ancient technology, autonomous planetary systems, and the quiet guardianship of a civilization that has long since spread beyond its birthplace. Earth's surface is no longer a center of population. Instead, it has become a world of memory and continuity. Vast natural preserves stretch across continents, protecting ecosystems that once depended on lunar tides and stable seasons. Artificial circulation systems still move ocean waters. Atmospheric processes regulate greenhouse gases. Climate stabilizers soften the sun's increasing intensity. These systems operate with minimal human intervention, guided by self-correcting intelligence networks designed to function for millions of years. Small caretaker communities remain scattered across Earth. Their role is symbolic as much as practical. They serve as witnesses to the planet's final natural era, monitoring its systems and preserving its history. These communities live lightly, drawing energy from fusion and solar collectors, recycling all resources and maintaining the delicate balance between technology and nature. For the rest of humanity, Earth has become a sacred origin world. Most people now live in orbital megastructures, on Mars around distant gas giants, or in artificial habitats orbiting other stars. Interstellar colonies thrive in nearby systems, carrying Earth's genetic archives, languages, and cultural traditions across the galaxy. Humanity has become a civilization measured not in nations, but in star systems. Despite this expansion, Earth's influence remains central. It is the foundation of humanity's identity. Every school across human space teaches the story of Earth's evolution from its formation to the moment the moon disappeared, and through the long transformation that followed. Students learn how planetary stability once depended on fragile cosmic conditions, and how intelligence eventually replaced natural balance with responsibility. The moon's disappearance is remembered not as destruction, but as awakening. It is taught as the moment humanity realized that no world is permanent, no orbit guaranteed, and no environment eternally stable. This realization reshaped civilization's values. Long-term thinking replaced short-term ambition. Cooperation replaced isolation. Preservation replaced exploitation. Cultural traditions across star systems still reference Earth's ancient sky. Festivals commemorate the age of moonlight. Virtual reconstructions allow people to experience lunar eclipses, tidal coastlines, and silver-lit nights that no living human has ever seen in reality. These experiences are not entertainment alone. They are reminders of the fragile conditions that once made complex life possible. As the sun continues its slow transformation, Earth faces increasing challenges. Even with planetary control systems, surface temperatures rise gradually. Oceans lose some of their ability to regulate climate. Atmospheric composition requires constant adjustment. Scientists predict that within another billion years, maintaining Earth's surface habitability will become increasingly difficult. Humanity prepares for this future calmly. Plans are already in place to transition Earth fully into a protected planetary archive. Automated systems will continue maintaining climate balance, preserving ecosystems, and recording geological and biological data. Human presence on the surface will become ceremonial rather than permanent. Earth will not be abandoned. It will be preserved as a living record of planetary evolution. A world maintained not for survival, but for knowledge, memory, and respect. Some philosophers argue that this moment marks the completion of Earth's role in humanity's story. It is no longer the center of civilization, but it remains the origin of consciousness that now spreads across the stars. Others believe Earth will always remain emotionally central, regardless of where humanity lives. As interstellar civilization grows, humanity encounters new worlds with different environments, different atmospheric conditions, and different planetary dynamics. The lessons learned from Earth's transformation guide every new settlement. Terraforming projects become more cautious. Ecosystem preservation becomes standard practice. Redundancy and adaptability are built into every habitat. The moon's disappearance echoes across this future. It becomes a universal symbol used in education, art, and philosophy to represent change, impermanence, and the responsibility of intelligent life. Across distant star systems, monuments are built honoring Earth as the first world. These monuments display models of the Earth-Moon system as it once existed, reminding future generations of the delicate balance that allowed life to emerge. Human identity evolves into something broader than planetary origin. People now identify as members of a living network of worlds. Yet Earth remains the emotional anchor. It is where humanity learned to walk, to think, to dream, and to survive planetary instability. In Earth's preserved forests, animals continue to roam. In protected oceans, marine life still moves through currents guided by artificial circulation systems. Mountains rise and erode. Volcanoes occasionally reshape landscapes. Earth continues evolving, even as human presence fades. Automated observatories record every change. Data streams flow across interstellar networks, allowing people light years away to witness Earth's storms, sunsets, and seasonal shifts. Earth becomes the most studied planet in human history, not because it is useful, but because it is meaningful. As the final caretaker generation prepares to leave permanent surface habitation, a global ceremony takes place. Across Earth and distant colonies, people pause to acknowledge the planet that gave birth to their civilization. Messages are transmitted across star systems. Virtual skies display Earth's ancient moonlit horizon one final time. This moment is not marked by sorrow alone, it is marked by gratitude. Gratitude for the oceans that once carried life, for the forests that shaped the atmosphere, for the moon that stabilized Earth long enough for intelligence to emerge, and for the planet that taught humanity how fragile existence truly is. After this moment, Earth enters a new phase. It becomes a preserved world maintained by autonomous systems and occasional scientific missions. Humanity's center of civilization shifts fully beyond the solar system. Yet Earth's story does not end. It continues quietly, evolving beneath artificial skies and natural stars, shaped by time, gravity, and the echoes of the life it once supported. The moon is gone. The planet is changed. Humanity has moved outward into the universe. But Earth remains, not as a forgotten world, not as a ruined planet, but as the silent foundation of a civilization that learned how to survive cosmic change. And somewhere across the stars, every human civilization carries this truth forward, that even when the sky loses its oldest companion, life can endure, that even when balance disappears, intelligence can create new stability, and that every world, no matter how temporary, can shape the destiny of the universe itself.